In this tutorial, we just want to look at the titration curves and make sense of them. So first of all, we'll have to talk about the different curves that we have, and then we'll look at just three interesting questions that will help us to understand whatever we're going to talk about. So first of all, what is a titration curve? So we know a titration curve is basically just a graphical representation of the pH of a solution during a titration. So we know titration is a reaction between an acid and a base. So we're trying to observe the changes to our pH as we get to either add an acid to a base or a base to an acid. And of course, we know that we have what we call strong acids, weak acids, strong bases, and also weak bases. So those diagrams of those different titrations get to give us different curves. Okay, so now if you look at this curve that we have here, what are we able to see? So what we are observing is initially the pH was somewhere below 2, and after addition of a certain volume of a substance, we've seen that there was an increase in what? In the pH, up to somewhere 14 there. Okay, so what comments can we make there? What comments can we make? So the fact that we are starting from the pH that is below 7 and of course less than 2, it shows that we are dealing with what? We add a strong acid present there. So we add a strong acid, and from our observation we're able to see that obviously what we were adding was basically what? Was basically a base. So if we add a base, we expect that there should be an increase in the pH. And of course we can have two different what? Two different curves. Let me try to show two different curves of the same where we are starting with an acid. So the other possibility that we can have is probably something that may come out like this, and then even ends slightly somewhere there, slightly after 7. So what comments are we able to make? So where we're starting from, this is of course a strong acid in both cases, and then what we're adding differs. So a case where it will just be slightly above 7, we call that a weak base. And then where we are going even up to above 12, up to closer to 14, that's a strong base obviously. So in this case, like the curve that I drew, which is in red, we used a strong what? A strong base, which is sodium hydroxide. Okay, so you should be able to tell on a pH curve or a titration curve where you're starting from and where you're ending. You should be able to tell what was used. Is it an acid? Is it a strong, or is this a strong or a weak base or an acid, depending on what you're dealing with in your titration? And of course, where you start from tells you what you add initially and what was being added to what. So assuming if we add a curve which was starting from 14 there, let me first of all just try to create some space before we could talk about that. So let's picture this. Okay, something like that. Now let's say we are starting from the top. Okay, and then we get to drop like this. Then we get to, and then like this. Okay, so of course in this case, the fact that we are starting above 7 and of course closer to 14 tells us that initially we add a strong base. Okay, so that is what you need to know. Where it is starting from tells you what you add. So in this case, what was being added was an acid because the solution is reducing a bit by bit until we get to an acidic region. So where you're starting from and where the curve is ending tells you whether you add a base or you add an acid. Okay, so now that we know the general way in which we expect these curves to come out, let's try to understand some of the key terms on this curve. Okay, so I'll go back to the curve that we had initially. Okay, so we had something that was showing us having a base, sorry, an acid, and then something like that, became something like that, and then went up like that. Okay, so if you've noticed, there should be this point where there's a bit of some lagging. It's reducing slowly, and then becomes a bit constant, the volume becomes, without even adding any more volume or any more of our sodium hydroxide, we'll observe that there's going to be this point where the volume is constant, you've not added any more, but you've seen that there is a change in the pH because the pH is changing. Okay, so that point there, we call it the equivalence point. It's very, very important to understand that. So that is called the equivalence point, a point where the number of moles of the base is equivalent to the number of moles of what? The acid. So at that point, that is where complete neutralization gets to occur. And of course, if you get to talk about the half of that, so half the volume of equivalence point will give you, just like the name itself, it will be half the equivalence point. Okay, so now at half the equivalence point, at that point, this is something that is very interesting about it. At that point, at half the equivalence point, of course, what you need to understand is the pK at that point is basically equal to what? Is equal to the pH. So if you are able to draw a line at the half equivalence point, it gives you the pH on the right hand side, because on the right hand side we can on the left, sorry, there is our pH there. So if you have your pH, then you know what is your pK. And of course, if we get to talk about the relationships that are there between the pK, we know that the pK being equal to pH at the half equivalence point, we know that this pK is also equal to the negative log of what? The negative log of Ka. So if you have a pKa, you should be able to find what? You should be able to use the value of pKa and find the Ka. So don't be surprised when they ask you to find the Ka. We've given you a titration curve. We're going to look at examples that are going to help us understand more. Okay, so we can now look at the questions that we have. So the question says, from the graph at the right, determine if the acid or bases are strong or weak. Okay, this is our diagram. So we can observe the initial pH that we had. So the pH was somewhere closer to 1. And then after adding our base, we've seen that it's somewhere up to 13. Okay. So what comments can we make? So of course we are very much assured to say it is a strong what? It is a strong acid. And obviously from what we are saying, the pH has gone very high. So for us to move a strong acid to somewhere up to 13 tells us to say that we also had a strong what? Base there. Okay. So another comment that we can make is we can say it was a strong acid and a strong base because of a steep vertical region that we have centered at pH 7. So usually when you have a strong acid and a strong base reacting, you expect that if you look at the equivalence point, of course, which is this one, the middle point is usually 7. Okay, that's also one key that you can look at. So that is the way you approach the first part there. Okay, very, very simple. Now, from the graph, again, B says determine whether the acid or base was added from the billet. So from what we are looking at here, where do we have our pH? pH started from 1. Now, after adding a certain volume, we had noticed that the pH was increasing. So what can you say? What was being added? So from what we are seeing is the flask contained the acid, and then we were adding a base, right? Because we've seen or observed an increase in what? In our pH. Okay. So that's what we can say. So we were adding, it was basically a base that was being added to what was in the flask there, or a beaker, or whatever was being used. And then C says the volume required to reach the equivalence point. So the equivalence point is basically where we're observing a steep in our graph here. So in this case, it is this part. So if you draw a line going down, it's going to give you a volume there. And from what we are observing from our curve, it's 10 milliliters. That's how much of a volume was required for us to reach an equivalence point. Okay. We can move now. And then this says the pH at the equivalence point. So you can find the pH at an equivalence point by looking at, first of all, where the steep started from. So looking at our curve, the steep is starting from somewhere there, 5, ending up to somewhere we can say 10. So in between, you can just go for the middle pH when you look at what? That part. So it's 7 in this case. So the pH at the equivalence point was 7. Okay. So the center of the vertical region, which is showing the equivalence point, that is your pH that you should consider. And then it says, determine the concentration of a base used if the titration started with 50 milliliters of an acid. Okay. So in this case, what have we been given? We've been given the volume, and then we've been given an acid that we started with, and then we've been told to determine the concentration of what? The concentration of, let's say that's the hydroxide that was being used. So what are we supposed to do for us to get to find that? Okay, so we know that at an equivalence point, we expect that the number of moles of our acid is basically supposed to be equal to the number of moles of what? Of our base. Okay, so from the information that we have, we know that our acid had 50 milliliters, and then of course we'd want to convert that to liters by dividing by 1000, because that's what we want to work with. So divide that by 1000, so say 50, our volume, by 1000, which will give us liters, and then multiply by the concentration, which is 0.05 molar concentration, which is the same as mole per liter. So we have a number of moles for our acid, and then for our base, we've been, what information have we been given? So from our diagram there, we had noticed to say what we had was 10 milliliters as the volume of what? So at equivalence point, this is the point that we're talking about. So we had a volume of 10 milliliters, and of course you'd want to divide that by 1000 as well. So that is 10 over 1000, and then this is in liters multiplied by the concentration that you're trying to find. So I can put even C there to denote that. And then performing our calculations there, what basically are we going to have as our concentration? So after performing our calculations, we find that our value of C, or the concentration of our base, is going to be 0.25 molar concentration from our calculations. So that's how we approach this question. Basically, the key things to take note of are the equivalence. At the equivalence point, the number of moles of our acid is basically equivalent to the number of moles of what? Our base. And of course, the middle point of the equivalence point gives us a pH at that equivalence point. So let's move to a second question. We are now on the second question. So from the graph, we are supposed to determine the following. A says if the acids or bases are strong or weak. Okay, so let's try to observe the curve that we have. Where are we starting from? We are starting from somewhere 4 there, and then we are going to somewhere up to 13 there. What comments could we make? Is it a strong acids? And of course, looking at where we are ending, that is very easy to tell. We can clearly see that we are ending up to somewhere where we have a strong base there. So we had a strong base. Now, somewhere 4 there. Is it a weak or a strong acid? So we can say it's a weak acid. Okay. And that can also be explained using this steepness that we have. Looking at the equivalence point, it's not as steep as it was when we had a strong acid and a strong base. So there is that. So this is not straight. This is not completely straight. There is this part and that part making it to be squatty. So this is a reaction between. Looking at where we are ending is a strong base. So obviously we had a weak acid. Okay, that's what we can say for this question. So we had a strong base and then a weak acid. Even looking at the pH, we're able to make a decision there. So we've answered A. Now B, we need to tell whether it was the acid or the base that was being added from the bullet. So from what we are seeing here is, since the pH is increasing, initially we had an acid. So basically in the bullet we had what? So it was basically the base that was being added from the bullet to our flask. C says the volume required to reach the equivalence point. So the equivalence point is where the volume is constant, and then we observe an increase in the pH. So in this case, we can clearly see that it's this region there. So that the volume gives you 15 milliliters as your answer there. That is an equivalence point. And then the pH of the equivalence point, you need to look at the middle part of that region that I've drawn a line. Okay, so I can remove that line so that we can see what we're going to have. Let me remove that. So we're saying 15 milliliters, of course. So this region is kind of starting from there and then ending at that point. So the middle part is somewhere there. Okay, so what value can we talk about there? What value can we talk about? So straightly we can say it's something like 9 point something. Okay, yeah, so somewhere there you can draw a line. So 9 point something. So of course, looking at the curve, if you have a ruler, it's going to be more accurate as you get to draw on your paper. And then it says the region where the buffering basically gets to occur. So where do we expect the buffering to occur? So buffering, of course, we know a buffer solution. What we expect for a buffer is there is basically no or little change to the pH. So what we are saying is, if you look at this curve, where is that region where we are seeing little or no change in this case? So we can show that by looking at the pH values. Okay, so we can see that somewhere from here there was little or no change in terms of our pH. Okay, so therefore, what basically can we say? So we can say from the pH of 4 to the equivalence point near pH 9, there we had observed a buffering region. Okay, so we've seen little or no change. So this part, so starting from a pH of 4 up to the equivalence, slightly before up to the equivalence point, we had observed little or no change in terms of a pH because of the resistance that we had. So we can call that to be the buffering region. And then if you look at F, which says the volume and the pH at the half the equivalence point. So half of the equivalence point basically is half the equivalence point as it tells. So if the equivalence point was 15 milliliters, half of 15 is 7.5. And we know that the value that lies between 5 and 10 is obviously 7.5. So that is half the equivalence point. So the volume at half the equivalence point was 7.5 milliliters. And then what else do we know? We now know that at half an equivalence point, the pKa is equal to the pH. So there, in this case, of course, the pH was just 5 if we look at the information that we have. So the pH was about 5. Okay. And then if they had asked us to find the pKa is also equal to 5 in this case. And then you can, in case where you have, they also want you to find the Ka, you can use this to help you find that, because you know pK is also equal to the negative log of Ka. And then if it is equal to 5, you can basically simplify this. Divide both sides by negative. That one becomes a negative. Take the 10 the other side so that you have your Ka being equal to 10 to the power negative 5. So that's how you handle this question. And now we are on the third question. This is a bit different. Why? Because what we have is we are starting from up going down. So it's a bit interesting than these other first two questions. Okay, so we need to determine whether we had strong acids or weak acids as our question area. So from what we're observing, we are coming from a value that is somewhere 9 closer to 7. So is it a strong base? We know, is it a strong base or a weak base? So we can clearly see that it's a weak base. And then what else can we observe? Or is it a strong acid? Where are we approaching? We're approaching even up to 1. That is a clear indication that we had a strong acid there. Now, what were we adding? So we are coming from basic medium going to acidic. So initially we had the base. Now after we are increasing the volume of our acid, so therefore we are adding an acid because of what we are observing. We are observing a reduction in our pH values there. And then C says the volume required to reach the equivalence point. So obviously the equivalence point is this part. Okay, right? So there our answer is what? 20 milliliters. And then this says the pH of the equivalence point. So what would you say about the equivalence point? So the equivalence point, if I was to erase this line that I've drawn, and then we try to observe clearly where it started from, where it is a bit straight from that point to this point. So the middle part is obviously somewhere there, which is going to give us a pH of a 4. Now, where did the buffering occur? So if we try to observe, where do you expect the buffering to have occurred? So initially from where we started, there was little or no change in our pH until we reached somewhere near the equivalence point, right? Okay. So we can just talk about this entire region from the pH of equivalence point up to where we started from. So we can say from 9 to 4. That is more like the buffering part because there was no reduction. There was little reduction in terms of the pH, changes in the pH, despite adding a lot of volume. What are we observing? Yeah, just adding, because look at this point, for example. We've added about 5 milliliters of our acid, but the pH is still low. It's still high, sorry. And then you continue to add more. It is still low. You add more again, it's still low. Just small reductions. That's basically what we are talking about. Now, after the equivalence point, you notice that just a little addition of the acid, you observe a very drastic change in the pH. Okay. And then question F says the volume and the pH of the alpha equivalence point. So if we know that the equivalence point from our diagram is this region where we are seeing the steepness, where it is 20 milliliters, half of that gives us what we are calling the alpha equivalence point. So that's the line that I've drawn. So the volume of alpha equivalence point is obviously going to be 10 milliliters as half of the actual equivalence point. And then what else do they want us to find? They want us to determine the pH. So the pH, of course, if you draw a line there against the curve, it is somewhere 7, right? So a pH of 7 at alpha equivalence point. So that is obviously also, I'm trying to emphasize, also equal to the pKa. Okay. And one more thing, just in case you've forgotten from what we said. So at alpha equivalence point again, what you need to realize is the number of moles of the acid is equal to the number of moles of your base. Okay. So this marks the end of our tutorial. I hope that you now understand how you can approach questions on the pH curves. So thank you very much for watching. You will have a lovely day.